We just mentioned that some of the elements might be repeated. Sometimes, not only could the elements be repeated, but the number of each kind of elements is limited. It's called permutation of multisets. Let's look at this problem. How many permutations are there for word ping pong? P-I-N-G, P-A-N-G. There are repetitions in this word. How many letters are repeated? There are 2 P's, 2 N's, and 2 G's. The number of these repeated elements are limited. We don't know how to calculate permutations of multisets, but we know how to calculate permutations without repetitions. So could we turn these repeated elements into different ones? Actually, it's quite simple. For example, label the 2 P's as P1 and P2. After calculating the permutation without repetitions, we could get the permutation of multiset by dividing the redundancy rate. Well, we label the 2 P's as P1 and P2, N, N1, N2, G, G1, G2, and I, A. Now we just calculate the permutations without repetitions, and the result should be 8 factorial. What's the redundancy rate? For P, there are 2 P's, so it's 2 factorial. N, 2 factorial. G, 2 factorial. So now we could deal with permutation of multisets. We denote it as Pn, add a semicolon, then use R1, R2, and so on to denote the number of each element. For the word ping pong, it contains 8 letters, in which there are 2 N's, 2 G's, and 2 P's. So we write it as 82211. For such a permutation of multiset, after labeling, we could know that the number of permutations without repetition is 8 factorial, then divided by the redundancy rate of each element, divided by 12 factorial, 2 factorial, 2 factorial. Finally, we could calculate permutation of multiset. The result is 8 factorial divided by 2 factorial, 2 factorial, 2 factorial. It's the number of permutation for ping pong. Not only could the method we just used deal with the permutations of English words, but also a lot of other things. Especially, we could apply it to polynomial expansion. In order to use it more generally, we have given it a formal definition. What is permutation of multiset? For multiple elements R1, R1s, R2, 2s, until RTTs, the total number of elements is n. The permutation is denoted as Pn R1, R2 until RT. It's equal to Pnn divided by R1 factorial times R2 factorial times until RT factorial. We could understand it as dividing the permutations of n by the arrangement of labels after labeling the repeated elements. Now let's rethink binomial theorem with it. Binomial theorem, a term in the expression of a plus b to the nth power, is a to the kth power times b to the n minus kth power. The coefficient of each term is actually equal to a permutation with repetitions, in which there are k's and n minus kb's. Of course, we could label all the k's and all the n minus kb's. According to the permutation of multiset we just studied, the coefficient of this term is equal to n factorial divided by k factorial and n minus k factorial. So we just viewed the binomial theorem with another perspective. Could we extend the theorem to the exponential of more than 2 terms? Maybe we could deal with a1 plus a2 until at to the nth power. How would its coefficients be? A term of its expansion is a1 to the r1's power times a2 to the r2's power until at to the rt's power. The coefficient of this term is the number of the arrangement of permutation of R1 A1s, R2 A2s. According to the calculation we just conducted, the permutation of n is n factorial, so is n factorial divided by r1 factorial times r2 factorial until rt factorial. Thus, we could get the coefficient of term in a polynomial expansion. Next, let's look at a game. This game is quite popular at game centers. Let's take ping pong balls as an example. There are 6 tracks which are corresponding to 6 holes. Now, we have 9 balls with labels 1, 2 until 9. We'd send them into 6 different holes via the corresponding tracks. If order matters, how many arrangements are there for the balls to go into the holes? This problem looks complex. It seems that there are a lot of situations. Let's analyze it. According to the order, the 9 balls are distributed into 6 areas. How should we represent these 6 areas? Actually, we have a masterly method, with it called the bar method. To obtain 6 area, we need 5 bars to partition it. To sending the 9 balls to the 6 area in order is equal to that there are already 6 area, and we are going to fill 1, 2, 3, 4 into these areas, like this. This in animation is an arrangement. So, how should we denote such arrangements? Actually, the bars are the same. But all the other elements, which are numbered 1, 2 until 9, they are different. It seems that in this permutation, there are both non-repeated element and some repetitions there. We just learned in permutation of multiset that if there are repeated elements, we have good method, which is to label the repeated elements and then divide the total number with the redundancy rate. It's the same here. Although all the bars are the same, we could label them, so we convert this problem into a permutation without repetitions. So now we find out that this problem is actually quite simple. And first, there are 5 bars and 9 numbers. So there are a total of 14 different elements. They form a permutation of 14, which is 14 factorial. Then we need to divide it by redundancy rate of labels. So factorial divided by 5 factorial is the answer. It gives us a new idea that for some partition-related problems, we could use the bar method to find the answer easily. Some of you might not be familiar with this method. Are there any other method? We would also do the partition, and then we could try to analyze by steps to obtain the answer. As we already have 6 areas, how many choices are there for the first ball? It might be in area 1, area 2, or area 6. There are totally 6 ways. After settling the first ball, let's see. This is a situation for the second ball. How many areas are there now? Actually, ball 1 partitioned an area into 2. So for ball 2, it might be at the left of ball 1 or at the right of ball 1. So in this situation, there are more arrangement for ball 2. It could be sent to 7 different positions. So forth. After ball 1 and ball 2 are settled, there are 1 more choice for ball 3. There are 8 areas for it. So forth until the last ball. How about the last ball? There are 14 choices for it. So the answer is to multiply from 6 to 14. It's equal to 14 factorial divided by 5 factorial, which is the same as we got by the first method. So we found that although the concept of permutation is simple, there are a lot of skills there. For problem with limitation of adjacency, we need to bind some elements together. For problem with multiple area, we usually use the bar method. Of course, there are many other methods. Hopefully, after practicing, we could find more skillful method. Next time, we could introduce more methods for combinations.